Hello and welcome, SFU Math 152, Calculus 2. It's Brenda Davison. This is section 11.8, Power Series. So maybe in some sense, I find infinite series really interesting, but part of the usefulness is now that we have the idea of infinite series as being sums of numbers, what we can do now is introduce a variable and see how we can represent a function as an infinite series. And what we're going to start with is an infinite power series. This is a very powerful idea, and it can be used in many different ways. So we're going to start with this. This is a big idea, hard to overplay the importance of this one. Okay, so polynomial, let's start with that. It's not the so lowly polynomial. Polynomials are highly important and useful functions. The polynomial looks like this. This is an nth degree polynomial when n is a non-negative integer. And then the coefficients here, we've called them, they're constants, they're just numbers, C0, C1 to Cn. Those are called the coefficients of the polynomial. So similarly, what we can do is basically just extend this out and let n basically go to infinity, and then then what we have is we don't call this a polynomial anymore, we call it a power series, and it is a function that looks like this. It has coefficients on each term of x, and it has the powers of x to the 0, x to the 1, x to the 2, x to the 3, and it keeps going. X is a variable, and the numbers C0, C1 are constants, and they're still called the coefficients. Okay, so this is in powers of x. We could also have the power series in powers of x minus a. So here we have x minus a to the 0, x minus a squared, x minus a cubed. So when we do it like that, we say that the power series is centered at a. That's yeah, one's a shifted version of the other. Okay, so let us just take a first look at the most basic power series, and then we'll look at something a little bit more complicated. So I think the most basic power series is when we set all of the coefficients to 1. So let's take a look at this. This is 1 plus x squared plus x cubed plus ... Okay, and what does that equal? I mean, so that is one way we could write a function. You want to calculate f of x, we could write it, f of x looks like this, equals the sum of n equals 0 to infinity of x to the n. And for example, if we wanted to calculate f of 1/2, we would go like this, or 1/2, oh sorry, that is not, that is the next term. We would go 1 plus, and we would substitute, just like we do for any other function. We want to evaluate when x is 1/2. We replace all the x's with 1/2. So this would look like this. And then we would have 1/2 squared plus 1/2 cubed. And in fact, we already know what this is, what this number is, right? What number is that? So that number is 2. Okay, and so we could see the function like this, or we have learned, in fact, that this particular power series here is the geometric series, and I could write this as 1 over 1 minus x, and we know that it converges when x is, the absolute value of x is less than 1. So I picked a value of x for which it converges. I could, of course, if take this function, f of x equals 1 plus x squared plus ... and I could evaluate it at x equals 2, which would look like this: 1 plus 2 plus 4 plus 8 plus 16 plus ... and then we would conclude that that diverges, and then it wouldn't make sense to have this description of the function be valid in the terms of the normal ways of converging at x equals 2. So final thing I want to just show you is we could come up with this formula here because we've already done this, the geometric series where a here is 1, the first term, and then the common ratio is x. Okay, because each time to go from one term to the other, we multiply by x. Okay, there's another way of determining that. If we look at this, or at least going the other direction if we wanted to do this, if we looked at this, 1 over 1 minus x, we could see that as a division, which it is, 1 divided by 1 minus x, and we can in fact do that via long division, like that. And you notice that normally when you do polynomial division, you put the highest power of x first. In this case, I'm going to put the lowest power of x first. I'm going to say, how many times does 1 go into 1? It goes in there 1 time. And then I would go 1 minus x, and then I would subtract and get x. And I would ask, how many times does 1 go into x? 1 goes into x, x times. And then I would multiply here, and I would get x. Trouble with the pen there. X minus x squared. I would subtract, and I would get here x squared. Then I would ask, how many times does 1 go into x squared? And I would get x squared here, and that would continue on. So I could go backwards from this thing here to this thing here via long division. It's our geometric series. Okay, so let's take a look now at another infinite series here, and we're going to ask for what values of x does this series converge? So it may converge for all values of x, it may converge for no, or maybe one value of x. It'll clearly converge when x is equal to 2, because then all the sums are 0. So, but maybe that's the only value, or maybe there's some values of x, or maybe all values of x. So the important thing to notice what's happened here is different, is we now have a variable. Prior to leading up to now, we only had numbers in here, and we were just saying, okay, if we add up all these numbers, what will happen? And now we're saying, okay, we've got numbers, but also we've got a variable, and that number will be fixed, and then we'll ask for that number, does it make sense to evaluate this infinite series? And then we can change x to another number. Does it make sense? And then we can just broaden that question and say, for what values of x does it make sense to assign a number to this infinite series? Okay, so it's really important that we notice that x is a variable. X is a variable, and x can be any real number. For some choices of x, I'm going to write this out. For some choices of x, the series will converge, and for others it will not. Okay, so our goal here is going to identify which values of x for which this series will converge. We are going to use the ratio test. Often we are going to use the ratio test, and sometimes we're going to be using the root test. But in this type of a question, often, this should be the first one that occurs to you, often use ratio test. Sometimes use root test. Okay, let's see how this is done. So I'm going to use the ratio test. AN is this thing right here. So I'm going to take the limit using the ratio test. What do? I take the limit as n goes to infinity of the absolute value of AN plus 1 over AN. And in this case, that looks like this: minus 1 to the n plus 1, x minus 2 to the n plus 1, divided by n plus 1 times 4 to the n plus 1. And then I divide by AN, which I'm multiplying by then the reciprocal here. It's not a to the 4. What am I doing? It is 4 to the n. And then we have minus 1 to the n, and we have x minus 2 to the n. Okay, so then I do my algebra on this, try to simplify this down. It's in its absolute value, so I can just, these things are going to be gone. I see, let us see here. I have x minus 2 to the n plus 1 in the numerator, and I have that in the numerator, and I have that in the denominator. So there's one additional x plus 2 in the numerator. So I have an x minus 2 here. And then I see I've got, what else? I've got n here and n plus 1 here. So I'm going to put those there, n plus 1. And then I've got 4 to the n divided by 4 to the n plus 1. That is simply 4. So this simplifies down to this here. And look like that. And I have forgotten, and I don't want to do that, to put here the limit as n goes to infinity. Okay, I haven't taken the, forgot it here too. Let's make this neater. I haven't taken the limit yet. Okay, so I want to take the limit as n goes to infinity of an plus 1 over an, and I've simplified this down a bit. And now when I look at this, I can take the limit with respect to, just changing my color here, with respect to n. We're taking the limit as n goes to infinity. That means these things here are simply constants with respect to n. So when I'm looking at the limit, I'm saying, okay, what happens when n goes to infinity of n over n plus 1? That limit is simply 1. So the answer here is the absolute value of x minus 2 over 4. So, and we know the ratio, so that's what we get when we take this limit. And we know for in the ratio test, convergence happens when this number is less than 1. So I'm just reminding you of that. Ratio test. We get convergence when this guy is less than 1. Okay, so now I can figure out what that is. That's when this guy is less than 4. And when is that? That is when x minus 2 is less than 4 or greater than minus 4. And then I could add 2 to all sides. So that tells me that x will be between minus 2 and 6. Okay, so I know that for values of x between minus 2 and 6, this series converges. We don't have any information of what happens when x is minus 2 or 6 because the ratio test is inconclusive when the ratio is equal to 1. So let's make a note of that. We have to check the endpoints separately. No information at x equals minus 2 or x equals 6 because the ratio test is inconclusive. When the ratio equals 1. So what I'm saying here is if I take this thing right here and I put in 6, I'll get 6 minus 2 over 4, and that's equal to 1. That I don't get any information from the ratio test. So I'm going to take a look at x equals minus 2 and x equals 6 separately. So I'm just look at those two numbers separately. Look at x equals minus 2, x equals 6 separately. Okay, so let's do at x equals minus 2 first. What we're looking at is the sum from n equals 1 to infinity of minus 1 to the n, minus 2 to the n. So I've put x equals to minus 2 right in, n 4 to the n. And then I do a bunch of simplifying here, and I see that that is minus 4. So we'll get the minus sign out, and that will combine with this. Maybe I'll do another step here, I think. Once I start talking too much, I think, okay, that'll look like this, minus 1 to the n, and then it will look like this, minus 1 to the n times 4 to the n over n times 4 to the n. And then these two things will cancel out. These two things will cancel out, and it looks like this. Okay, and what series is this? Okay, so it diverges. This is the harmonic series, diverges. Okay, then I take a look at the other endpoint. That is x equals to 6, and I do exactly the same thing. I get n equals 1 to infinity minus 1 to the n. Here instead I get 6 minus 2 to the n over n times 4 to the n. So we need to be really careful with the minus signs, because here I just get this, minus 1 to the n, 4 to the n over n times 4 to the n. This cancels out, and I have here this series here, n equals 1 to infinity, minus 1 to the n over n. That's the alternating harmonic series, and so we know that this one converges from earlier analysis. This one diverges. Okay, so that tells us what's happening at the endpoints. So then I can answer the original question. Therefore, x in the set minus 2, but not including minus 2, up to and including 6, the series converges. Okay, so that means it means we can have a function that looks like this, some function. There it is, and that's how we're going to calculate the values of the function, just like this. And it has a domain of minus 2, 6. Okay, so we use the ratio test to understand the convergence of the infinite series for values of x. We want to know for which values of x does this thing converge, and then if we're thinking of this as being a function where we would give a certain value of x, and then we would get an infinite series which we would evaluate and get the value for the function, we will do so for values of x in this interval. That's the domain of the function. Okay, we can have functions that appear in a variety of different physical situations in different manners, and we can have the function defined by an infinite series. So when a function shows up in a lot of useful context, usually it is given a name, and for example, sine or cosine or tangent, those functions are given names because we find them to be useful in lots of different places. Here is another function. This function does not have a definition, perhaps like you're used to seeing, but this is actually a function definition. You have some rule. Given an input x, you have a rule for finding the output. That's a function. And the rule that we have is this calculation involving this infinite series. This function is called the Bessel function of order 1. And we're asking here, what is the domain of this function? So just so, I don't know, for your interest, I mean, the Bessel function shows up in, for example, electromagnetic waves calculations. So when you're doing in physics, it shows up in heat conduction. This is a really important function. You could, in fact, go on Wikipedia and just Google Bessel function, and then you could take a look at the graph of it. That would be kind of interesting. It shows up in membrane vibrations. It shows up sometimes in friction calculations. It shows up in signal processing. It's all over the place. Okay, so this is an important function, and we want to know for what values of x do we get a convergent infinite series when we're attempting to calculate this. So we're going to again use the ratio test. So let's make note of that. Use ratio test. So I'm going to compute that limit. The limit as n goes to infinity, the absolute value of an plus 1 divided by an. And so I'm going to put an plus 1 here. That's going to be minus 1 to the n plus 1 to x to the 2. Be careful with the brackets like this so that you make sure you substituting in n plus 1 where n is, and you've got the brackets on to indicate that properly. N plus 1 factorial. Then n plus 1, and when I'm putting in here n plus 1, then I get here n plus 2 factorial, and then I have 2 to the 2 n plus 1 plus 1, and then I am dividing by an, which is multiplying by the reciprocal of an, so I get here n factorial, n plus 1 factorial, 2 to the 2n plus 1 divided by minus 1 to the n, x to the 2n plus 1. Okay, now it's absolute value sign, and I'm going to try not to I'm not ready to take the limit yet. So it's absolute value, so I can get rid of those things. And then I look and I have to just see what's happening. I've got n plus 1 factorial, so that's gone. And then I have n factorial over n plus 2 factorial. So I'm looking then at, where am I? Oh, I'm just going to circle this with a different color. Maybe see what is happening here. So now I'm looking at here, the n factorial and the n plus 2 factorial. I can simplify that down to this, n plus 2 times n plus 1. That gets me those two things there. I'm looking then at, let's look at the powers of 2 we have. We've got 2 to the 2n plus 1, and we're dividing that by 2 to the 2n plus 3, leaving me with 2 squared in the denominator. 2n plus 2, yeah, 2n plus 3, yep, leaving me with 2 squared. And then similarly, it's the same calculation here, these two here, leaving me with an x squared in the numerator there. Okay, so I am simplifying it down. Go slowly when you do these simplifications. You want to, it's easy to like lose something, and then of course the entire conclusion can be wrong if you've yeah, if you lose an n plus 1 or something like that in this calculation, you're toast. Okay, so let us look then at what we're doing. Can we take, well, I'll just write it out without the absolute value signs. We've got 4 times n plus 2 times n plus 1. Now I'm thinking, what happens when n goes to infinity? The denominator gets huge, and it doesn't really matter what x is. This will be equal to 0, which is less than 1, and that happens for all x. Okay, x is some number that we put in there. So then I draw the conclusion that the Bessel function of order 1 converges for all values of x. Okay, so then we would say J1 of x has domain minus infinity, infinity, or all real numbers. Okay, this is here, all real numbers. Okay, so it converges. Okay, so sort of summarize what we've been talking about here. Where does the power series converge? Okay, so we're given a power series. There's 3 possibilities. Converges when x equals a, because all the terms are 0. That's unexciting, and we generally don't see those very often because, well, like we're not getting much out of those. Converges for all x. We just saw an example of that right here. That was the Bessel function of order 0, converged for all x in R. The other possibility, there's some number R such that the series converges when x minus a is less than R and diverges when x minus a is greater than R. Notice there's not saying anything about what happens when x minus a equals R. Okay, right here. So this was our first example, this case here, our first example in this lecture. And in that example, we had R equals 4. The radius of convergence was 4. Okay, so we specify 2 different things here. The radius of convergence, we just talked about that. And then we also have the interval of convergence. That consists of all the values of x for which the series converges. So in our first example, just to notice what the difference was, we had r equals 4, the radius of convergence was 4, and the interval of convergence was from -2 to 6. Okay. So if you look at something centered at 2, I mean, we're thinking centered at 2, then you can go 4 on either side. So the interval is from -2 to 6. Okay. That is, yeah, that's the two cases we've seen. Okay, let us use this newfound terminology and ability to do a few examples. So basically, maybe pause, even think, maybe try these yourself. What we're trying to do here is enlarge our view of the word function. So we've previously had, you've seen functions for a long time now. We could have a function, you know, y equals x squared. And now what we're saying is, okay, that is still a function, of course, but now we're saying we can actually enlarge our definition of a function, and we've seen now we could have a function. In fact, we've seen more than one enlargement. So this would be a sort of more basic example. Then we've also seen this kind of a thing, for example. So we could see a function that looks like that, where we have the variable as the upper limit of integration, and now we're saying we can do this. Like that. Okay. Where those CNs are constants. So we're sort of wanting to get used of seeing functions in a way that we haven't seen them as frequently. In fact, because we've also talked about the differential equations, we already in some sense also, for example, could see a function this way. For example, that is the exponential function. This one right here. That's the exponential function. We are going to see that we can in fact write the exponential function as a infinite series. That is coming soon. That's a big moment. And we for example, could write the exponential function like this. And it's the same function no matter which way we write it. So this is exponential function. We have one of these for the exponential function. We're going to see what those constants need to be, and we could write it this way. Okay, so we're kind of enlarging our view of the word function. So we're now going to try to find the interval of convergence for these following series. Okay, I'm looking at, let's look at question A. We're going to see what the interval of convergence is here, and I see this both to the power of n here. So I think to myself, maybe looking good here would be the root test. That's what I'm thinking to myself, so let me try that. So I'm going to use the root test. I'm going to take the limit as n goes to infinity. The limit as n goes to infinity of the nth root of the absolute value of a to the n. And in this case, that is the limit as n goes to infinity of n to the n, x to the n, to the 1 over n, and that is n times the absolute value of x. Okay, so what happens? Oh, I did it again. Okay, I haven't yet taken the limit. Let's not forget that. So this is n times the absolute value of x. Okay, so now I want to take that limit. What is that limit? The limit as n goes to infinity of n times the absolute value of x. Well, I mean, this is fixed at some number, and then n just grows arbitrarily large. So that is infinite. So for all values of x except x equals 0, which of course then we have the limit as n goes to infinity of 0, which is 0. So the I would write then this, the interval of convergence is in fact just the set containing 0, and the radius of convergence is 0. Okay, so this is an uninteresting series because we can do pretty much nothing with it. It only converges when x is 0, and we can see that f of 0 is 0. So I mean, that's that. It's not very exciting. Okay, let's take a look at B. This is the sum as n goes from 1 to infinity of x to the n over n times 3 to the n. I may think to use the root test. Why don't I just try that? I'm going to get unhappy with that and probably move on, but it doesn't matter. Let's just see what happens. Try the root test. So I say try root test because I see those powers. It's not an unreasonable thing to do. I see the nth power here. An is x to the n over n times 3 to the n. And so I would then take a look at the nth root of the absolute value of a to the n, see what that looks like. That looks like this, x to the n over n 3 to the n to the nth root. And then that's going to look like this, absolute value of x over 3, 1 over n to the 1 over n. And I see this, I look at this and I'm like, that's a bit of a hassle. It's still going to work, of course, but I see this as hassle to take limit of this. As n goes to infinity. You can see it's 0 to the 0. You have to fiddle around and use L'Hopital's rule and take the limit. So then I might instead try the ratio test. You may want to actually just complete this as an exercise. So you, again, just to try to build up the efficiency factor and get a sense of which things are typically faster. So that's going to here be an plus 1. So I'm setting up to take the limit of this then, and that is going to be x to the n plus 1 over n plus 1, 3 to the n plus 1 times the reciprocal of an, which is this here. And then I do my algebra on this, x over 3 n plus 1, and then caution with these absolute values. Okay, so that's the absolute value of x over 3 times n. N is positive, 3 is positive, n plus 1 is positive, but x could be positive or negative, so we cannot just remove the absolute value signs. That absolute value signs must stay on here. So now I'm going to take that limit. I'm going to take the limit as n goes to infinity of absolute value of x over 3 n over n plus 1, and then this portion here that is affected by the changing value of n is ratio of two polynomials, so of the same degree, so we can use the limit's going to be the leading coefficient, so this limit is going to be the absolute value of x over 3. We know that because we're using the ratio test, this thing has to be less than 1, which means the absolute value of absolute value of x has to be less than 3. That means that x has to be between minus 3 and 3, like that. So immediately once I'm here, I know that the radius of convergence is 3. Okay, now if I want to know what the interval of convergence is, I have to check the endpoint. So I don't know what's happening at minus 3 and 3 at this point. I don't get any information from the ratio test, so I need to take a look at the endpoints separately. So I'm going to do that. Check endpoints. When x is 3, I get, so I substitute in 3 directly into this thing, and I get this guy here, 3 to the n over n 3 to the n, and it is our friend, the harmonic series. There it is, and we know that that diverges. Okay. This happens all the time. So I put such much emphasis on this earlier on. The harmonic series diverges. You want no hesitation when you see that. Okay, let's check the other endpoint minus 3, then this will become the sum n equals 1 to infinity of minus 3 to the n over n 3 to the n, and that will simplify to this. And that's the alternating harmonic series, and as we know, that converges. So it converges at the left endpoint, but not at the right endpoint. So then I can write here that the interval of convergence is this. Converges at minus 3, does not converge at 3, and converges everywhere in between via the ratio test. Okay, let's do the final example, part C. That is going to be this one here. Okay, I see that factorial there. Also, I'm basically inclined to more generally try the ratio test. It seems to be nicer to use most of the time. So with the combination of those two things, I'm going to use the ratio test. So I'm going to do exactly what I've done the last several times I've done this. So why don't you actually, because you've seen me just do this twice, why don't you stop the video and form this ratio, do the algebra, take the limit, and see for what values of x does this series converge, and then turn back on the video and see if you're right. Okay, so I'm going to take the n plus first, a to the n plus 1. And then I'm going to divide by an. And then I'm going to carefully do some algebra. In fact, I'm thinking I want to be careful about this situation here. This and this. I have to be a bit cautious. Let's take a look at that in maybe a bit more detail just below here, so we can make sure we see how this is working. So I'm going to be simplifying this, and I want to do a good job of that because I don't want to draw the wrong conclusion here. So let me just write this in this way, 2n factorial, and then I'm going to distribute that 2, and I'm going to get 2n plus 2 factorial. And then that's going to look like this, 2n factorial divided by 2n plus 2, 2n plus 1, and then 2n factorial. Okay, so I mean, if you're not convinced of this, I mean, not that that would be a proof, but try, I don't know, with n equals 3 or n equals 4, and assure yourself that you see what's happening when this canceling is happening. So that is going to then cancel with that, and this thing here is 1 over 2n plus 2 times 2n plus 1, like that. Okay, so I can then retreat back to the calculation of I was making with that stuff I can fill in. So I've got that an plus 1 over an is then equal to, let's see, minus 2 times x divided by, so that's x to the n plus 1 divided by x to the n is simply x. And then I've simplified that other part of it separately, so I know that this is this here. I put that in. It's in absolute value. And so that is the ratio of the two things. So now I want to take the limit. I'm going to take the limit as n goes to infinity of this thing, of this guy right here. And just while I'm doing that, I'm going to take away the absolute value sign. So I'm going to make this, this will be 2 times the absolute value of x divided by, and I'm going to multiply this out. That's going to be 4n squared plus 6n plus 2. Okay. So what happens when n gets really, really large? This is going, for any fixed value of x, this is going to go to 0, which is less than 1 for all x. So the radius of convergence here convergence is infinite, and the interval of convergence is minus infinity to infinity. So this thing converges for all values of x. And let me just rewrite this one down here as a final point on this example. Here's what we looked at. An infinite series like that. Okay, we've determined that this converges for all values of x. So I could, for example, let me just label this like this, f of x. So I can calculate, if I want, f of 10, and f of 10 would look like this. Okay, and should I be able to evaluate that, I will get some number, and that number will be f of 10. Now I'm going to tell you something, sort of a preview for what's coming. And actually, this function f of x, this function right here, which I've labeled f of x is in fact equal to this cosine root 2. That's not root 2, is it? It's root 2 root x minus 1. That is in fact the exact same function as this. Okay, so were I wanting to calculate this f of 10 like I did earlier, I could go like this, cosine of square root 2 times the square root of 10, and then subtract 1. Or I could do this thing here. I can put in 10 there. I could add up, for example, the first 1,000 terms and get an approximation. So you could see, for example, in your calculator, you could in fact have the formula, like an infinite series formula for the cosine. And when somebody enters cosine of something, what do you do then? You could calculate the requisite number of terms of your infinite series such that you get an answer accurate to 8 decimal places or 10 decimal places, whatever your calculator displays, and then you show that to the person, and that's what they see, and they're like, hey, there's the cosine. I mean, think about that. How else, in fact, at this point in your career, how else would I be calculating this? You imagine me entering this into a calculator, I get a number. How does the calculator do that? I mean, it's not a lookup table, that's for sure. Okay, so that's what's coming, and then that is the power of this thing. I'm able to go back from between what we're maybe more used to a representation of a function to its infinite series representation. And then that allows us sometimes this version will allow for easier approximation, perhaps because it's just a polynomial, an infinite polynomial or power series. We can integrate it term by term or differentiate it term by term. Maybe these things are easier because we've effectively turned something that we may find more complicated into a polynomial of power series. Okay, so there's some really big ideas here. Might be a good idea to sit back at the end of this lecture and sort of think about try to get for yourself the sort of bigger picture. Okay, we spend some time learning about these things called infinite series, seem to be just adding numbers together. Sometimes we can add them together and get a finite number, sometimes we can't. Now suddenly we've introduced a variable into the situation, and then now suddenly we're getting a new vision of what a function might be. We may be getting clues towards numerical methods for doing calculations. There's a whole bunch suddenly coming with this new idea. So seeing functions in different ways, it's a very important topic. So try to puzzle through this, get used to it, and then if there's questions, certainly, especially conceptual questions, please bring those up in my office hours and scheduled lecture times. Okay, that's all for today, and we'll be back and learning some more about this interesting topic. Thank you. Bye.